Hi, today we're going to look at a new video by Professor Kyle Adams from the Flat Earth Institute of Science, and he's going to tell us all about gravitational force. I first of all like to say massive thanks to all my members, patrons and subscribers. I want to give massive thanks to all of my supporting members and patrons. Thank you all so very much. Okay, Professor, tell us all about it and roll VT. Okay, Kyle, show us your new teachings.
Alright, let's talk about gravitational force. Not too long ago, I had a conversation with an anti-flat earther by the name of MC Toon.
Nice guy. He's not anti-flat earther. If you could come up with the evidence, I'm sure he would be pro. We just need the evidence.
He told me that if the Earth was flat, gravity must not exist.
I think it's more the other way round. Because gravity does exist, the Earth cannot be flat. But proceed.
So I asked him, what makes you think that?
Science, teachings, maths, understanding?
He said it had to do with something called the potato radius, and he provided a link that explained it in further detail.
Cool.
He said anything over a certain mass or size has enough mass to collapse into a spherical shape. Larger masses are more spherical. The critical size is between 200 and 300 kilometers, depending on the composition.
Well, just imagine you've got a quantity of a substance attracted to itself or drawn to itself. The smallest shape it can be in is a sphere.
That made me think of the Rocky Mountains, which are 4,800 kilometers long. And so I asked, so you claim mountains should collapse into a spherical shape instead of a flat one?
Well, mountains
generally, from what I've seen, erosion causes mountains to level.
Mountains are part of the Earth. So with the rest of the Earth, it's all trying to collapse into a spherical shape, apart from the other forces acting on it, such as the bulge caused by the rotation of the Earth.
Out, not turn into giant potatoes. His response was, not mountains, the entire Earth.
There you go. Everything on the Earth is trying to collapse towards the middle, and the smallest shape is a sphere.
Well, so much for his 200 and 300 kilometer thing. I wanted to hear him out though, so I asked, if it all collapses, what is the determining factor that determines the central collapse point, and what makes you think that factor exists on the flat Earth model?
Well, all particles are drawn to each other. As you get clumps of larger particles, they'll exert greater attraction. I'll show you why in a minute. And so gradually over time, as bigger and bigger clumps clump together, they all compact into one solid mass. As for the flat Earth, well, you guys need to tell us what your model is. This is a gravitational simulator. It enables you to simulate the effects of gravity on objects. So if we scatter loads of little dusty particles all over, and then we'll place a number of larger objects, we can see what happens. The path of every object is affected by every other object. They start attracting each other. When two objects meet, their combined mass then exerts a greater attractive force on the masses around it. Basically, over time, these objects gather in clumps. It's called accretion. The bigger something gets, the faster it gets bigger, and you end up with one object. You can see how the larger objects are basically cleaning up the surrounding space, gathering everything else to them. Take a lump of clay. Stick another lump of clay to it and you've got a funny shape. Stick a third and a fourth and a fifth lump to it. As you keep adding lumps at random over the outside of that collection, it will look more and more like a sphere. The larger the object, the more spherical it will look. If objects are falling and joining on with your lump of clay at random, I defy you to end up with a flat disc.
And that is where his straw man argument was exposed. He was inventing his own model and saying, see, it doesn't work.
I don't think he was inventing his own model. I'm not sure that MC Toon, clever guy though he is, I'm not sure he came up with gravitational theory and so on.
Not too long after that, I went and took the same questions to another anti-flat earther.
I also am not an anti-flat earther. I'm pro whatever the evidence shows. And unfortunately, the evidence does not show a flat earth. Therefore, I cannot support it. If you guys come up with the evidence, I will support it if that evidence is better than the evidence for a globe. Anyway, what on earth did I tell you?
That I know, by the name of Mr. Sensible.
Subscribe.
And thankfully, he was quite a bit more sensible with me.
I am sensible, but let's see how you respond to my sensible comments.
When I asked him, where is the middle center of gravity on the flat Earth?
What did I say?
He said, well, depends on the model, I guess.
Yep.
Say a disk with an ice wall.
Yes,
and the center would be the North Pole, then halfway through the thickness.
Yeah, if you assumed that the material of the Earth was pretty much constant throughout, that would be true. If you had loads of iron ore in one area and lighter materials in another area, then that would shift the centre of mass. But generally, yeah, it would be the centre of the disk and halfway through the disk.
That left me to ask, that depends on whether or not the Earth stops at the ice wall, doesn't it? Also, isn't...
Well, that's true, but, it's your model. We don't think it's a flat shape at all. So I guess you guys need to explain whether it ends at the ice wall or continues on forever.
Density a factor on where the center of gravity is?
Absolutely. Like I said, if you've got lots of dense material in one area, that will shift the centre of gravity.
If I had a weight attached to one end of a ruler, I couldn't say that the center of gravity on that ruler is still in the center of that ruler.
Yep.
And that is where he refocused things and said, the point is, wherever the center is, gravity would be pulling things toward it, and everything would collapse into a sphere. And that is where his straw man came out.
No. If you had a perfectly smooth and uniform disk, and it wasn't being rotated aggressively, then it may be able to maintain its shape. But it's natural materials. You're going to get weaknesses. You're going to get thicker areas like the sort of mountainous areas and deep chasms and so on, all introducing stresses and strains, and it would collapse into a sphere.
According to his model, there was no way his flat Earth could have a balanced center of gravity.
It's not my flat Earth. Don't you go blaming me for it, Kyle. But that's right. You're going to get differences. So you'll get different stresses and strains. If you've got an area with lots of mountains, they're going to pull towards the rest of the mass harder than areas that are thinner and so on. And when I say pull, don't take that literally.
Now, something that really stood out to me about both of their descriptions of gravity was how they both described it as a force that pulls on things.
Yeah, that's just the vernacular. You can treat it as though it's a force that pulls on things. It appears as though it's a force that pulls on things. That's the effect.
This directly disagrees with what Einstein taught us about gravity. According to Einstein, one of the happiest moments in his life was when he realized gravity and acceleration are the same thing.
Yes, they are. And one of the happiest moments in my life, of course, was when I met Mrs. Sensible. But that's another story.
As physics of the universe paraphrases, gravity is in reality not a force at all, but is indistinguishable from, and in fact, the same thing as acceleration.
And I would not disagree with that.
Here's a little clip from Nova that talks about that.
He imagines a man in a box, floating weightlessly in a distant region of space, in zero gravity. Suddenly, the man stops floating and accelerates downward until he's standing in the box. What has happened?
Tell us.
Either the box is now close to a planet, and the force of gravity has pulled the man to the floor, or someone has attached a rope, and the box is now being pulled continuously and accelerated upwards.
Note that word, accelerated.
So which is it? Gravity or acceleration?
Hard to tell when you're in a box.
Without being able to see outside, the man can't tell what's causing his fall to the floor.
Einstein realized that there is no way to tell the difference between sitting in a gravitational field and being accelerated. And these are equivalent situations.
The fact that these two effects are the same, give the same result, means that gravity is acceleration. It's not just like acceleration, it's the same thing.
It's a big breakthrough.
Right, now Kyle, I don't know if it will be a surprise to you, but the idea of universal acceleration is nothing new. It's an idea that has been around for a long time in the Flat Earth Society, and it doesn't work. I'll let you carry on for a few seconds and then I'll tell you why.
This is why we refer to the acceleration we feel in a car as g-force. And I see no reason why acceleration would not be able to exist on the flat Earth.
Right. Yes, g-force. 9.8 meters per second is one g. If from a standing start, in 1 second you reach the speed of 9.8 meters per second, during that first second you have experienced 1g acceleration. But that's the important word, acceleration. Because a second later, you mustn't still be going at 9.8 meters each second. You must have accelerated by another 9.8 meters per second, bringing your velocity to 19.6 meters per second. Then after 3 seconds, you're at 29.4 meters per second. 4 seconds, you're at 39.2 meters per second. It's an acceleration. You must keep going faster. The real problem with that is, apart from the fact that something needs to provide that acceleration, to provide that force, within 1 year, you'll have approached the speed of light. Doesn't work, Kyle.
The last time I checked, g-force doesn't care what shape the Earth is. Although, if Einstein is right, and the Earth's gravity effect is being caused by the Earth's acceleration, that could create some problems for the globe Earth model.
Einstein is not saying that the Earth is accelerating. Einstein is saying that the gravitational effect that you experience is an acceleration towards the centre of the Earth. You need to think of it as a net, and I'll show you what I mean. Imagine the fabric of space and time just as a flat net of squares. Objects in space actually bend the fabric of space and time. The larger the object, the greater it warps it. If you're a ball rolling across that net, you travel in a straight line. If you got close to the Earth, your path would be bent by that warping of space-time. It will look as though the Earth has pulled you off of your path. Your path would then be deflected slightly. If you passed even closer to the Earth, your path would be deflected even more. Basically, you're trying to roll down towards it. That's the effect of gravity. Of course, space is a three-dimensional environment, so imagine it as a stack of those nets, making little cubes, and the warping is stretching those cubes nearer to the Earth more and more. The closer you get to the Earth, you'll find that the net has been warped more and more, so you will continue accelerating towards the Earth. Here you can see lots of objects, each of which are warping space and time to a greater or lesser extent. The larger the object, the greater the warping. Now, if you try and roll a ball from the top of the screen to the bottom, you can only imagine how the path of that object will be diverted left or diverted right. And if it's too close to one of those dips, it will roll all the way into them. The object isn't pulling the ball in, but the object's warping of space-time is causing the ball to roll towards it. That's the gravitational effect.
This is an instance where gravity, which is acceleration, would not cause water to stick to a ball. Unless, of course, the Earth is accelerating outward in all directions, in which case the Earth would have to be perpetually exploding.
And it would get further and further to travel to work every day. Good job that's not the answer, isn't it, Kyle?
At this point, I often get people who shallowly say, "Yeah, well, you just don't understand."
Yeah, well, you just don't understand.
So let's hear PBS describe this Einstein principle in their space-time show to verify my understanding.
Yeah, let's see if you do understand it, Kyle.
Isaac Newton said that an apple falls because a gravitational force accelerates it toward the ground. But what if it's really the ground accelerating up to meet the apple? Suppose I drop an apple. According to Isaac Newton, the ground can be considered at rest, Earth applies a gravitational force to the apple, and that force causes the apple to accelerate downward. But according to Einstein, there's no such thing as a gravitational force. Instead, it's more appropriate to think of the apple as stationary, and the ground, along with everything on the ground, as accelerating upward into the apple. Now, what I just said sounds preposterous and maybe even moronic, but it's not sophistry. There's something substantive here.
No one can accuse me of creating a straw man argument here, or misrepresenting anyone, when they are the ones directly making the claim.
You could think of the apple moving towards the Earth. You can think of the Earth moving towards the apple. There is an acceleration at 9.8 meters per second per second. What it's caused by is caused by the bending of space-time, as I showed in those nets. It's like a ball is rolling downhill into a well, into a dip. Here is an excellent explanation and visualization by Carl Coriolis.
I call it the space-time stretcher. It's basically a graph for charting the up or down motion of an object over time. Now pretend for a minute that there's no gravity. If we let go of an object, it would just float there. Time would pass, but it wouldn't go up and it wouldn't go down. On our graph, it would follow a flat line along the time axis only. We can represent that line with a strip of colored tape. This is what happens as time passes. The apple stands still. Add some gravity and see what happens. Gravity is like a bending of this graph of space and time. And we can make that happen by turning this handle. The more we turn it, the more our space-time graph gets warped, corresponding to stronger gravity. Let's repeat what we did earlier, now with gravity. If we let go of an object, it starts along the same horizontal line as before, moving only through time. Only now, space-time is warped. Notice that while the object is following the same flat line, now the time axis is peeling away. Let's return the space-time stretcher to neutral. Following each object across time, now the apple, instead of just floating there, starts to move downward, and it accelerates as it goes. This is how gravity works. All freely moving objects follow straight paths through space and time. But if space-time is warped, as it is where there's gravity, then those paths appear to change. Let go of an object, and even though it's passing only through time at first, the warping will cause it to begin moving downward through space as well, completely on its own. And an object tossed upward will slow down, stop, change direction, and return to where it came from.
This is where gravity is described as a fictitious force.
Right, let's hope you understand the word fictitious. Go for it.
And yes, fictitious here directly means non-existent, pretend, or imaginary.
Non-existent? True, there isn't a force, but there is a very, very real effect. An effect that you can see, feel, and measure, to the extent that you can actually treat it as if it's a force.
It is just like Coriolis Force.
Yes, it is.
And centrifugal force.
Yes.
We can describe them. We can say what they do to other things.
Yep.
We can measure them,
Yep.
predict things with them.
Yep.
But these forces themselves do not exist.
That's true. Things like Coriolis, and I hope that you have a greater understanding of Coriolis than many flat earthers. Coriolis isn't a force. Nothing is pushing that cannonball sideways. The cannonball is continuing on in a straight line, but from the frame of reference where the cannon has shot it, it appears as though a force has pushed it sideways. Great stuff.
They are caused by something else.
Yes! Kyle, you've really gone up in my estimation. Please have a word with Flatzoid FE and Nathan Oakley and tell them that they're just stupid idiots.
All right. So it turns out there's no such thing as centrifugal force. It's the word we give to this thing that feels like a force operating on you if you are the water in that bucket, or if you're in that amusement park where I think they call it the cyclone, where you're sort of pinned against the wall of it and it rotates and you feel this pressure increase on you. So anyhow, so this centrifugal force, you will feel it as though it's a real force. And so that's why we gave it a name, all right? And by the way, Coriolis Force is another fictitious force.
See, Neil gets it.
It feels like it's a real force operating, but it's the product of other things going on. The Coriolis Force turns storms into...
in a clockwise...
counterclockwise
direction.
In the north and clockwise in the south.
Which is what we talked about last time.
Well, I'm sorry, Carl, I missed that. But yes, Coriolis, centrifugal force, they're fictitious forces. If you're on a roundabout, feeling as though you're being flung outwards, nothing is flinging you out. What is happening is you are trying to go in a straight line, but the centripetal force is keeping you in that circular rotation. And the counter to that is the fictitious force of centrifugal force.
And here's one more clip for you.
What is gravity?
I have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know.
There's no problem with that, Kyle. If you can use gravity in your calculations so that you can calculate the angle to fire a cannon, so that you can work out how a rocket is going to fly and so on, if those figures work in the equations, job done. The actual mechanism behind it, we want to know, but if we don't know right now, it's not critical. We can still successfully use it.
With that, while it may surprise you, I actually agree with him. Was Newton right, or was Einstein right?
They're both right.
Were they both wrong, or were they both right? I don't know. That is a mystery we are still trying to figure out, just like the rest of the world. And the major takeaway here is that gravity is not an issue with the flat Earth.
Only gravity is a major issue with the flat Earth. You need something to cause an upwards acceleration of that flat Earth, or you need something to cause objects to go down towards that flat Earth. And you also have to be concerned about the flat Earth not collapsing into a sphere. Additionally, if it didn't collapse into a sphere, and you have the centre of gravity, the point that everything's being pulled towards or falling towards, being the centre of that disk, that means by the time you get out towards the edge of the Earth, you'd be having to lean over more and more and more in order to keep your feet towards that centre of gravity. Flat Earth doesn't work, Kyle.
Thank you for watching.
My pleasure. Kyle, thanks for that video. I enjoyed that one. I'm glad that you, apparently alone amongst all the flat earthers, seem to respect that there is a thing called Coriolis Force, or effect, that is a fictitious force, i.e. not an actual force, but the effect of something else. What you do need to understand is it's an effect of the rotation of the Earth. Anyway, I hope you all enjoyed that. Until next time, stay sensible.
Shut up and sit down.